Risk-taking. One of the main points made by the skeptics concerns risk-taking by NASA. One would expect that the risk assessment was a primary cornerstone of NASA's design philosophy, as they had the lives of the astronauts to consider. By all accounts, the astronauts were never able to properly control the flying bedstead safely. Remember that the ungainly-looking contraption designed to mimic that landing on the moon would be light. One would imagine that it was essential to unequivocally demonstrate that such a spacecraft with a single throttleable gimbaled rocket engine, together with side thrusters, was a viable proposition before sending astronauts to go and try it on the moon. After all, it was a totally new type of vehicle, entirely unfamiliar to the astronaut pilots, never flown before, and could never be tested in space. Add to that the fact that the actual descent and ascent stage rocket engines could not be prior tested, then the risks are compounding. The skeptics ask, is it really conceivable that NASA would risk witnessing the deaths of the astronauts, presumably on live TV, in front of the entire world? If it were not possible to demonstrate clearly in the tests on Earth that the system was totally foolproof, does it make sense to tell the astronauts to travel 240,000 miles and give it a try on the moon? Who knows, it might work there? Of course, NASA's rebuttal is characteristically unambiguously simple. It did work perfectly well. In any event, the flimsy-looking spacecraft does not in itself disprove the moon landings. Too hot to handle. These violent delights have violent ends, and in their triumph die, like fire and powder which, as they kiss, consume. William Shakespeare, Romeo and Juliet. Radiation. On 7th August 1972, within the Apollo era, an enormous solar flare exploded from the Sun's atmosphere, along with a gigantic burst of light in nearly all wavelengths. This event accelerated a wave of energetic particles. The flare consisted of mostly protons with a few electrons and heavier elements mixed in. This wash of quickly moving particles would have been dangerous to anyone outside the Earth's protective magnetosphere. Luckily, the Apollo 16 crew had returned to Earth just 5 months earlier, narrowly escaping the powerful event. Seems as though they had a close shave. Unfortunately for us, radiation is a complex subject. Normally, I would say it was best left to the experts, but if we are trying to understand this debate between the skeptics and believers, then we must venture into this morass of science. The first problem is that there are a myriad of units used to assess the level of radiation. We have becquerels, curies, grays, sieverts, Roentgens, rems, rads, and a few others. Unfortunately, the conversion between these different units is not an easy task. So do not be too worried if you do not understand everything. I doubt that the effects of radiation on the moon are really understood by anyone, even NASA. The Van Allen belts. Here on Earth, we are surrounded by two regions of intense ionizing radiation called the Van Allen radiation belts, which are formed as a result of Earth's molten inner core, mostly consisting of iron. The spinning of the Earth results in it creating a giant magnet with lines of magnetic flux radiation far out into space. It is these belts of magnetic flux that trap most of the harmful radiation from the Sun and keep the Earth safe and protected. The belts were first detected by the American physicist James Van Allen in 1958, hence the name. He used balloons and rockets, referred to as rockoons, carrying instruments to measure the levels of radiation as these passed through this region. What he detected was that the radiation measured by the Geiger counter first increased and then dropped and suddenly increased again. From this, he deduced that there were two distinct belts of radiation. The Earth has a magnetic field with north and south poles, as we know from using an ordinary compass when we were a youthful Boy Scout or Girl Guide, or equivalent. This magnetic field occurs because the center of the Earth is still molten iron. This magnetic field reaches out 36,000 miles into space, into a region we call the magnetosphere. It is this magnetosphere that prevents most of the harmful particles from the Sun carried in the solar wind from reaching the Earth. Particles from the solar wind enter the magnetosphere and are directed towards the poles, causing the impressive displays of the northern lights, Aurora Borealis, and the southern lights, Aurora Australis. The magnetosphere is formed along the Earth's magnetic fields, which trap many of the charged particles and cosmic rays, and thus protect the Earth from a continuous harmful bombardment. The radiation belts are weakest near the Earth's poles and most intense around the equator. The question then, is it possible for humans to traverse these regions of radiation and remain unharmed with the same number of arms and legs, fingers and toes? It is on this basis that the skeptics make their case. They claim that the Van Allen belts are an impenetrable barrier, deadly to any spacefarer who attempts to traverse them, and therefore the Apollo missions could never have taken place. In consequence, they say that man never walked on the moon. We know that the astronauts on the Apollo missions never died from, or as far as we know, never suffered from, any form of radiation illness. So, if it were possible for humans to survive the Van Allen radiation belts, then Apollo was, at least in part, hoaxed regardless of what all other evidence suggests. The Van Allen belts are caused by mostly unpredictable solar particle emissions such as solar flares. There is evidence to suggest that major flares occur at their most savage according to an 11-year cycle. The general unpredictability of these solar flares implies that any space missions through the Van Allen radiation belts does carry an inestimable danger to the astronauts. Clearly, this would imply that NASA would have carefully studied the Van Allen radiation belts and concluded that it was not dangerous to send humans traveling through them. Paradoxically, 1969 was the height of the 11-year solar flare cycle, so the danger would have been in its greatest for Apollo 11, and it would not have been possible to pick a worse time to sojourn to the moon. It is interesting to note that what Van Allen himself said about these dangers of the radiation belts in the scientific paper published in Scientific America in March 1959, long before the Apollo era, which he states, "Our measurements show that the maximum radiation level as of 1958 is equivalent to between 10 and 100 roentgens per hour depending on the still undetermined proportion of protons to electrons. Since a human being exposed for 2 days, or even 10 roentgens, would have only an even chance of survival, the radiation belts obviously present an obstacle to spaceflight. Unless some practical way can be found to shield space travelers against the effects of radiation, manned space rockets can best take off through the radiation-free zones over the poles. There is even no agreement on the thickness of the Van Allen radiation belts. Van Allen himself estimated that they extended 64,000 miles from Earth, whereas NASA claims that they only extend to 24,000 miles. This may be academic, as even beyond the radiation belts, there would be total exposure to solar radiation particles with no protection from the Earth's magnetosphere. We need to try and get our head around this radiation business. We measure radiation with an instrument called a Geiger counter, named after its inventor, the German physicist Hans Geiger, in the 1920s. Radiation is measured in units called Roentgens, named after another German, Wilhelm Röntgen, who discovered X-rays in 1895, which he received the first ever Nobel Prize in Physics in 1901. 1 Roentgen is the amount of ionizing radiation producing 1 electrostatic unit of positive or negative ionic charge in 1 cubic centimeter of air under standard conditions. If you live in a typical city, say in Europe or the US, then you will be experiencing somewhere in the region of 10 to 20 microRoentgens per hour, mostly cosmic radiation and radon. Now for the maths. 1,000 microRoentgens equals 1 milliroentgen, and 1,000 milliroentgens equals 1 Roentgen, so 1 single Roentgen is roughly 100,000 times the average radiation of a typical city. I guess you're feeling better already. We need to try to understand that the level of radiation is harmful to our well-being. A dose of 500 Roentgens within 5 hours is catastrophically fatal to humans, but it takes about 1,250 Roentgens to kill a chicken and over 125,000 Roentgens to dispatch a cockroach. I always wondered why these pesky cockroaches survived all of my attempts to kill them. Now I know they are immune, even from a nuclear attack, so me chasing them with a shoe doesn't faze them at all. Remember above, Van Allen estimates that passing through the radiation belts would inflict between 10 and 100 Roentgens per hour, depending on the still undetermined proportion of protons to electrons. Astronauts would be in the Van Allen radiation belts, according to NASA, for approximately 2 hours each way, so they would receive a minimum of 20 Roentgens in each direction, and a maximum of 200 Roentgens in the worst case. He also states that a human being exposed for 2 days for even 10 Roentgens would have only an even chance of survival. Note that in our 10 Roentgens over 24 hours or so, 0.42 Roentgens per hour, and that would give a 50% chance of death. Our astronauts could have been exposed to a minimum of 10 Roentgens per hour, according to Van Allen. However, as always, it is not that simple given that the time the body can repair the damage caused by the radiation, for example, after you have an X-ray. Perhaps the fact that the astronauts would only be exposed for a couple of hours meant that any damage could have possibly been repaired. The other question that nobody seems to know is what is the situation when you have passed through the Van Allen radiation belts? It is certainly not safe out there either, with no safe protection from the Earth's magnetosphere. Just to make one thing clear, the Van Allen radiation belts do not cause the radiation, they simply stop the harmful radiation from the sun reaching the Earth. The real serious radiation problems may start on the other side of the radiation belts, so going to the moon could be a terribly sickly business. At first, this radiation belt argument may appear to be the deciding factor, which makes all other arguments about flapping flags, adulterated crosshairs, missing stars, temperatures, spacesuits, blast craters, moon dust, and so on rather superfluous. Unfortunately, it is also the one aspect that is the most difficult to determine and one of the most complex areas of space science. Radiation science is an extremely expert area, and it is probably reasonable to conclude that no conspiracy theorist possesses the expertise needed to correctly address the problem. So what is radiation, and how can it be protected against? It is well described by the believer Jay Windley on the Clavius website. Note that Windley uses the more modern radiation unit of the REM, which is just slightly less than the older unit of Roentgen used by Van Allen, so equivalent for our purposes. Simply put, radiation consists of these several types of particles: alpha particles, electrons, protons, X-rays, and gamma rays. Alpha particles are relatively large and do not penetrate deeply into many things. In fact, they do not even penetrate dead skin. A sheet of reasonably thick paper will stop all alpha particles. Protons penetrate further, but they can be shielded by light materials or plastic about 1 centimeter thick. Electrons and X-rays can be stopped with lead sheets, but this would need to be several inches thick and therefore too heavy to be transported into space with current rocket technology. Gamma rays are the most destructive to human tissue and need a minimum of 1 foot of lead sheet or 2 feet thick concrete. Damage to humans from radiation is cumulative. Small doses can be tolerated as the body has the capability to repair itself. Many of you will have had an X-ray. Did you notice that the radiographer ran for cover but left you there to suffer the damage from the X-ray? Radiographers have to do their job all day long, day after day, and would accumulate a high dosage if they stayed in the room holding your hand while the X-ray was in progress. You may have noticed that the radiographer has a dosimeter, like a small badge attached to their uniform, to measure the cumulative dose that they receive. The exposure of the X-rays for you was low, but necessary, dosage which your body would quickly repair. If you notice any extra fingers or toes sprouting, then immediately consult your doctor. The most dangerous types of radiation is referred to as ionizing radiation. It is this form of radiation that damages tissue, blood cells, and bone, and in sufficient quantities can lead to a quick and I guess unpleasant death. In radiation, we refer to dosimetry as a measure of the dose received. Dosimetry is an extremely complex issue, and there are several types of units of measurement which we will happily skip. The question is, how long would an astronaut be in the Van Allen radiation belt, and what is the dosage he would receive per hour in that area? We have estimates from Van Allen for the dosage level and from NASA for the time of the exposure, but nothing appears to be certain. As we have seen, radiation has many forms, some harmful to humans and some not. There have been many attempts to answer this question by skeptics and believers alike, with the obvious partisan conclusions, so we are left no further towards the truth. Radiation effects on the Apollo astronauts. It appears that NASA in the 1960s was not ignorant of the Van Allen radiation belt and the possible effects on the astronauts and did investigate what might happen. In order to monitor radiation exposure during the flights, Apollo crews carried a Geiger counter on board their spacecraft and dosimeters on their persons. At the end of the Apollo program, NASA determined that its astronauts had avoided the large radiation doses many feared would ground flights to the moon. NASA state that over the course of the lunar missions, the Apollo astronauts were exposed to lower doses than the yearly 5 rem average experienced by workers with an Atomic Energy Commission who regularly deal with the radioactive materials. NASA also states that in no case did any astronaut experience any debilitating medical or biological effects. So NASA claims that the Apollo astronauts received only a small amount of radiation during any of the Apollo missions for the following reasons. 1. Radiation protection in the spacecraft. 2. Protection from the EVA spacesuits. And 3. The short period of time of passing through the most intense area of radiation in space. The skeptics cannot understand that if the Apollo astronauts were completely safe and suffered no ill effects from their soiree to the moon, why now does NASA appear to have concerns about the astronauts on the latest Orion project passing through the Van Allen radiation belts for future missions? NASA are still actively studying the radiation problems of space travel outside low Earth orbit with the BIRD project. NASA have also produced a report concerning the radiation challenge to space travel entitled Spacefaring and the Radiation Challenge. In this report, NASA state, the major goal of NASA's Space Radiation Project is to enable human exploration of space without exceeding an acceptable level of risk from exposure to space radiation. Space radiation is distinct from common terrestrial forms of radiation. Our magnetosphere protects us from significant exposure to radiation from the Sun and from space. Radiation that is emitted from the Sun is comprised of fluctuating levels of high-energy protons. Space radiation consists of low levels of heavy charged particles. High-energy protons and charged particles can damage both shielding materials and biological systems. The amount or dose of space radiation is typically low, but the effects are cumulative. Solar activity fluctuates, and the risk of exposure increases with the amount of time spent in space. Therefore, there is significant concern for long-term space travel. Possible health risks including cancer, damage to the central nervous system, cataracts, risk of acute radiation sickness, and hereditary effects. Because there is limited data on human response to space radiation, scientists have developed methods to estimate the risk. This is based on theoretical calculations and biological experimentation. The skeptics are quick to point out that NASA says that it has limited data on human response to space radiation. I have underlined the sentence in question referred to above. They ask, after how 9-man journeys to the moon and almost 40 days of experience in deep space, can they still say that they have limited data on the subject? They remind us that the astronauts were there, they measured the radiation, but now they seem to have only limited data. NASA's response to that criticism, also in the above report, is this statement. It is important to note that the NASA Apollo program was designed to land humans on the moon and bring them back safely to Earth. It was not designed to establish a permanent presence on the moon. The duration of the lunar surface missions were very short, largely due to the risks of space radiation and exposure and the unpredictable nature of the solar weather. NASA have published the following table relating to the radiation dosages received by the Apollo astronauts, which shows that the astronauts did not receive large doses of radiation in any of the Apollo missions. For some unexplained reason, the astronauts on Apollo 14 received considerably more dosage than on any other Apollo mission. It could well have been an increase in the unpredictable solar activity, so for some reason, the Apollo 14 astronauts suffered the largest radiation dose of 1.14 rad. Your typical dental X-ray is about 0.05 rad, or about 1 day's worth of normal background radiation, so the astronauts suffered about 23 days worth of normal Earth-based radiation, which is equivalent to 2 chest X-rays. Therefore, according to NASA, a very small dose of radiation indeed. The skeptics wonder if this is really true, then why are NASA so concerned about radiation affecting future space travel? NASA are investing heavily on the research into space radiation with the Radiation Belt Storm Probes. In this document, they state, the Radiation Belt Storm Probes, RBSP, are twin spacecrafts designed to fly and operate in the heart of the most hazardous regions of near-Earth space and collect crucial data. That data will allow researchers to finally begin to unlock the mysteries of the Van Allen radiation belts, the two donut-shaped rings around the Earth made up of very high-energy electrons and protons that can damage satellites and endanger humans during spaceflight. Again, our skeptics have a problem to understand why NASA are still saying that they need to unlock the mysteries of the Van Allen radiation belts when they seem to have much less worry during the Apollo missions and supposedly proven that radiation was not as harmful as first thought. In an internet paper, believer Robert A. Breunig states, "Observations from the ground and from spacecraft demonstrated that the space radiation hazard was one of lesser engineering problems to have overcome in the Apollo spacecraft design and mission planning. Flux maps of the Van Allen belts were developed, solar flare particle events were subjected to intensive statistical analysis, and techniques were developed to calculate radiation doses behind complex spacecraft structure. Van Allen radiation belt doses were kept small by the use of low-altitude Earth orbits and rapid transits to the Moon along trajectories with inclinations of about 30 degrees. Only the very large and consequently very rare solar flare particle events consisted a hazard for moderately shielded spacecraft. Also, secondary radiation was not significant for such spacecraft. Most of the Apollo radiation protection's activity was directed towards providing protection against major solar flare particle events that might occur while astronauts were in the lunar module or on the lunar surface. The events, which start at the Sun, were detected by ground-based instrumentation and were measured at the spacecraft by dosimeters and particle spectrometers. A prognosis of the radiation dose was prepared and continually updated by radiation environment specialists using a console in Mission Control Center (MMC). Dose estimates were then provided for the use of the medical officers who advised the flight director of the radiation effects to be expected. Solar Particle Alert Network. The Solar Particle Alert Network, SPAN, or SPAN, was established by NASA to support the Apollo program. The network has 7 stations around the world, situated so as to provide 24-hour coverage of the Sun at both optical, weather permitting, and microwave frequencies. There were 3 stations equipped with both optical and radio telescopes: Houston in Texas, Carnarvon in Australia, and the Canary Islands. There were 4 additional sites equipped with optical telescopes only. SPAN's function was to monitor solar activity during these missions and provide warnings of particle events. Time of occurrence, area, and location of the flares were determined by SPAN observers and were teletyped to the MMC when the data were incorporated into the estimate of the particle event size. The radio burst profile was also teletyped to the MMC. Data from SPAN were augmented by data from the solar and ionospheric monitoring systems operated by the Environmental Science Services Administration and the Air Weather Service. NASA state that if SPAN detected that a large solar flare was imminent, there would be a few hours of advance notice of the particle flux. This was adequate time for the astronauts on the Moon to get back into the Lunar Module, LM, and take off, rendezvous with the Command Service Module, CSM, and take cover as best as they could. While in lunar orbit, the Moon would protect the astronauts from half of each orbit. At other times, the spacecraft would be turned so the bulk of the service module was between the astronauts and the incoming particles. The astronauts also had a handheld Geiger counter so that they could find the safest spot in the command module cabin should they have to ride out a solar flare. Given that the 3 astronauts only just fitted into the command module, I am not sure where they could find a safe place to hide. During Apollo's operational period of 1969 to 1972, there were only 3 solar events that had a biological significance, none of which occurred during a mission. Only one event in August 1972 was large enough to have caused severe illness, as we have mentioned in this previous video. Suffice it is to say that it is probably not feasible for the skeptics to tackle this problem scientifically. Rather than attempt to answer these complex scientific arguments, some skeptics have concentrated more on the logic of the discussion. The skeptics believe that with this level of investigation and the large investment in the Solar Particle Alert Network that we mentioned above, then the astronauts would have been well briefed, well trained, and knowledgeable about the Van Allen radiation belts, or so you would have imagined. They point to the fact that in the filmed interview, astronaut Alan Bean, the lunar module pilot on the Apollo 12 mission and the fourth man to set foot on the moon, was asked by Bart Sibrel about the Van Allen radiation belts. This discussion, say the skeptics, clearly shows that NASA could not have gone to the moon. The interviewer, Bart Sibrel, asked,
"Any ill effects from the Van Allen radiation belts?"
No. Now, I'm not sure we went far enough out to encounter the Van Allen radiation belt. Maybe we did.
Bart Sibrel then reminded him,
The belts are 1,000 miles to 25,000 miles above the Earth.
We went right out through them.
Bart Sibrel asks,
No effects on your cells?
to which Bean surprisingly replies,
We didn't even know it. I don't think anybody, well, maybe somebody said you went through the radiation belt, but we didn't feel it inside, and we didn't get any, added radiation.
Later in the same interview, he is asked about shooting stars. The interviewer comments that when the space shuttle went to 365 miles above the Earth, the astronauts reported seeing shooting stars. Bean then comments,
We saw shooting stars, but they're not shooting stars from with your eyes closed, although they look like it.
but unbelievably, a few moments later he states,
My guess is in Earth orbit, if you closed your eyes and just paid attention, that you would see them. But see, if you're just going to sleep or closing your eyes or it's dark, you don't notice them. But if you'll close your eyes and pay attention, which we had an experiment to do, by the way, then you see them whistling by. Not on our mission, by the way, they hadn't been discovered yet.
seems you could not see them because they were not yet discovered. Interesting statement. This totally contradicts what he said previously, that he saw them, and that then he did not see them because they had not been discovered yet. Incredibly, in the next sentence, Bean then says,
I saw them one day on the moon. It wasn't dark, and it was kind of dark, and I saw this flash of light, and it looked like it was on the moon, but really it wasn't. It was a flash of light in my eye.
Is it any wonder that the skeptics have a problem of belief? The skeptics argue that one would expect more assured answers from an astronaut pilot supposedly trained to take a flight path to minimize exposure in the Van Allen radiation belts, trained to use his Geiger counter, trained to maneuver his spaceship to avoid solar flares, and having a dosimeter affixed to his spacesuit to have been slightly more knowledgeable about the subject? Perhaps he missed the day they discovered that. Of course, you may well argue that it was a long time ago, and we humans do forget with age, but this seems a hardly plausible explanation. NASA's next generation of spaceflight missions is named Orion. The objective of the Orion project is to explore planets away from Earth, and it sights the Moon and Mars. A recent NASA video designed to promote the Orion spacecraft has been commented upon by the skeptics. This video discusses the testing procedures for the Orion spacecraft and states that one of the aims of the test procedures is to send Orion through the Van Allen radiation belts. It states, radiation like this could harm the guidance systems on board computers or other electronics on Orion. Shielding will be put to the test as the vehicle cuts through the waves of radiation. We must solve these challenges before we send people through this region of space. Naturally, the skeptics are more eager to point out that this was supposedly done with the Apollo project, so why now are there new concerns on this matter? It is for them clear proof that the Apollo missions never traversed the Van Allen radiation belts, and therefore man has never reached to the moon. NASA refutes this argument and offers the following explanation. Firstly, the Orion spacecraft contains much more complex and sophisticated electronic equipment than the Apollo systems, which could potentially be damaged by radiation, and so has to be tested before humans are allowed to fly inside it. Secondly, Orion is not solely intended to go through the Van Allen radiation belts and is back in a few short days as the Apollo missions did. It is designed for missions up to 21 days long and perhaps even longer if it formed part of a mission to Mars. As a result, the astronauts would face exposure to vast amounts of radiation in space, maybe for months on end, and so testing its shieldings is considered to be essential. In a letter published by James Van Allen, he states, "The radiation belts of Earth do indeed pose important constraints to the safety of human spaceflight. The very energetic protons in the radiation belts are the most dangerous and the most difficult to shield against, specifically prolonged flights. that is, one of many months' duration of humans or other animals in orbit about the Earth, must be conducted at altitudes less than about 250 miles in order to avoid significant radiation exposure. A person in a cabin of a space shuttle in a circular equatorial orbit in the most intense region of the inner radiation belt at an altitude of about 1,000 miles would be subjected to a fatal dosage of radiation in about 1 week. However, the outbound and inbound trajectories of the Apollo spacecraft cut through the outer portions of the inner belt and, because of their high speed, spent only about 15 minutes in traversing the region and less than 2 hours in traversing the much less penetrated radiation in the outer radiation belt. The resulting radiation exposure for the round trip was less than 1% of a fatal dosage, a very minor risk among the far greater other risks of such flights. I made such estimates in the early 1960s and so informed NASA engineers who were planning the Apollo flights. These estimates are still reliable. The recent Fox TV show which I saw is an ingenious and entertaining assemblage of nonsense. The claim that radiation exposure during the Apollo missions would have been fatal to the astronauts is only one example of such nonsense. However, the believers do contend that NASA did take the successful precautions to avoid the worst of the Van Allen radiation belts, for example, this by the believer Curious Droid, and also this from Amy Title on the Vintage Space YouTube channel. It is interesting to note that both of these believers explain that the path taken by the Apollo missions was a northern trajectory to avoid the inner Van Allen radiation belt composed mainly of protons considered to be the most dangerous for humans. Research by skeptic Scott Henderson may indicate a very different story as described in this video from Faking Space series. Scott Henderson has carefully researched what NASA said about the spacecraft trajectory back at the time of the missions. His important findings indicate the following. 1. No mention was ever made about this northern trajectory taken by the Apollo missions at the time, i.e. 1968 to 1972. 2. The highly detailed Apollo press kits, which explain each part of the missions, failed to mention this northern trajectory. 3. The published paths of the Apollo trajectories were always shown as being close to the equatorial plane. 4. The Apollo 11 press kit specifically states that the trajectory was just south of the equator when it made its translunar injection rocket burn. And 5. Perhaps most importantly, none of the Apollo missions transcripts have any mention of passing through the Van Allen radiation belts. If the Van Allen radiation belts were considered to be important enough to take a particular route north, then, one would expect, Mission Control would have mentioned how the astronauts were coping with the radiation and even asked for information from the astronauts on the Geiger counter readings or dosimeter readings, but there is absolutely nothing. And finally, the northern trajectory would have required considerably more fuel and a longer time, but no mention was ever made for this in the mission planning. From this investigation, Scott Henderson concludes that it was only after this event that the questions raised by the skeptics that NASA was forced to address this matter. This is a very revealing investigation and may even be seen as a smoking gun. Scott Henderson's conclusions are also backed up by a 1967 NASA video on the determination of launch window for the Apollo missions. Note that this video is dated 1967, just 12 months before Apollo 8 was launched around the moon carrying astronauts. There is no mention of radiation, no mention of avoiding the Van Allen radiation belts, and no mention of taking any special route other than the 28-degree envelope off the equator. Now surely, if minimizing passage through the Van Allen radiation belts was designated for, then this video from NASA would have surely made mention of it. The only information on the danger of the Van Allen radiation belts from the believers is to repeat the NASA northern trajectory explanation, which from Scott Henderson's work appears to have been manufactured after the event.